Namaste children, welcome back again to this virtual class. So in today's session we will be learning a new concept called electromagnetic induction. Before starting this, let us have a quick recap on what we have learned in the previous episode. We have seen the heating effect of electric current, and followed by that we have seen the magnetic effect of electric current. We learned that when electric current is flowing in an electric circuit, apart from heating effect, magnetic field will also be produced. We call it as magnetic effect of electric current. If the current carrying conductor is a straight one, then the direction of the magnetic field could be found out by using which rule? That is right hand thumb rule. We have used right hand thumb rule, right? Here in right hand thumb rule, thumb indicates the direction of electric current, whereas the fingers which are holding or which are wrapping around the straight conductor will be the direction of magnetic field. And if the current carrying conductor is a circular loop, there also same right hand thumb rule will be used to find the direction of magnetic field, right? But when we go from one end to another end, direction of or the position of our hand gets changed, but the direction of magnetic field appears to be changed. But when we hold the conductor, then we see the same rule is applied. Moving further, we have seen about solenoid. Solenoid is a coil of many turns of insulated copper wire wrapped in the shape of a cylinder, right? When we increase the number of turns of the conductor, the magnetic field will get increased. And we have also seen that when the magnetic materials are kept inside the solenoid, then the strength of the magnetic field gets increased. Now the solenoid is mostly used to magnetize the material such as soft iron. We call it as electromagnet. Altogether we can say that when electricity is supplied to a solenoid, then it acts very well as a magnet. We call it as electromagnet. Here one side will be north pole and another side will be south pole, just like a bar magnet. We have also seen when a current carrying conductor is placed in a magnetic field, then force is exerted on the conductor. To know the direction of force exerted on the conductor, we have used Fleming's left hand rule. Can you recall? In Fleming's left hand rule, we have to extend first three fingers in such a way that all the fingers make right angle to each other. They are perpendicular to one another. Now central finger indicates current, forefinger indicates magnetic field, and the thumb indicates motion. So by using Fleming's left hand rule, we can find direction of electric current, direction of magnetic field, direction of motion. So this is what we have seen in the last episode. So in today's episode, we will be seeing one of the most important topic in magnetic effect of electric current, that is electromagnetic induction. So we have learned that when a current carrying conductor is placed in a magnetic field, then force is produced. With that force, the conductor moves. Now the direction of electric current and the direction of the magnetic field are perpendicular to each other. In the Fleming's left hand rule, we have seen central finger for current and forefinger for magnetic field, both are perpendicular to each other, right? If they are perpendicular to each other, then the strength of the magnetic field produced will be more. Now think about a situation in which a conductor is moving inside a magnetic field, or the magnetic field is changing around a conductor. What will happen in such situation? This was first studied by an English physicist called Michael Faraday. So Michael Faraday made an important breakthrough how a moving magnet can generate electricity. To understand this, let us take some simple examples. From that you will be much clear about it. Now we have a simple electric circuit in which, in place of potential difference, we have connected a galvanometer. Dear students, we have learned that the flow of electric current in an electric circuit will take place if we apply potential difference. In absence of potential difference, we won't see any flow of electric current in the circuit, this is what we have studied in the chapter electricity. Now we have a simple electric circuit in which we don't have any potential difference. That means voltage is not applied, battery is not available, so obviously there will not be any flow of charge, right? In place of potential difference, I have used a device called galvanometer. What is the purpose of galvanometer? Galvanometer is a device which is used to know the presence of current in an electric circuit. Now, ammeter also we have used in the earlier case. In the chapter electricity, we have seen about ammeter, right? Ammeter is the device which is used to know the quantity of current that flows in an electric circuit. Then what is the difference between ammeter and a galvanometer? Ammeter is especially used to know larger current. For very smaller current, we use another device called galvanometer. There is another difference between ammeter and galvanometer. We cannot find the direction of flow of electric current, whereas in galvanometer we have the facility of knowing the direction of flow of electric current. If the needle deflects right hand side, then it indicates one direction. If it deflects other side, then the direction of electric current will be different. So this way we can easily find the direction of flow of electric current in an electric circuit by using galvanometer. When a magnet is brought near this circuit, it was observed that electricity is produced in the circuit, indicated by the deflection of needle of the galvanometer. The needle of the galvanometer will deflect only there exists or there produced any electric current. So when magnet is brought near this circuit, electric circuit, then the deflection we could see. This indicates that current is produced. So this is what Michael Faraday also observed. The current so produced in the circuit is what we call induced current. Here the current is not produced because of applied potential difference. Here we don't have any potential difference. Battery is not there, voltage is not supplied. Although we didn't supply any voltage, current is produced. The current so produced is because of we have brought magnet near the circuit. Whenever magnet is brought near the circuit, current is produced. The current so produced is what we call induced current, and the process is called electromagnetic induction. Here introducing magnet in near the circuit produces current, so we call it as electromagnetic induction. Here electro means electrons, magnetic means magnetic field, and induction means we are introducing the magnet near the coil, which ultimately generates electricity in the coil. Dear students, now look at the screen very carefully. Here is the magnet. When the magnet is moved around the conductor, as soon as it starts moving, when the magnet is in motion, you can see very well that the needle of the galvanometer deflects, and the deflection is towards right hand side, right? From this we can understand that when a magnet is moved around a conductor, electric current is produced in the circuit, and the electric current so formed is called induced current. Why it is called induced current? Here in the circuit we don't have any potential difference. Voltage is not being applied. We have learnt in the chapter electricity that electric current will start flow in an electric circuit only if we apply potential difference. Here we don't have any potential difference. But when the magnet is moved around the conductor, there electric current is generated. This electric current is called induced current. This is how we can understand induced current. Now see here, when the north pole is moved around the conductor, the direction of the needle of the galvanometer is towards right hand side. Now let us see what happens if south pole approaches the conductor. See here, when the south pole approaches the conductor, then there also we can see the deflection. The deflection is due to electricity. Electric current is generated in the circuit, but the direction of electric current is towards left hand side. So from this we can understand that on moving magnet or magnetic field around a conductor, electric current will be produced, and the poles decide the direction of the induced current. So far we have seen induced current is produced in the circuit when a magnet is moved around the conductor. What will happen if we keep the magnetic field stationary, that is constant position? We are moving the conductor in a magnetic field. In that case, you see, look at very carefully, here the magnet is at a fixed position. Now I am going to move the conductor in a magnetic field. Here magnet experiences its magnetic field. When the conductor is brought inside the magnetic field, then you can see again the needle of the galvanometer deflects, which shows that the movement of conductor in a magnetic field also produces electric current. This electric current is called induced current. In electromagnetic induction, when we move the magnetic field near the electric circuit, we could see the deflection of needle of galvanometer, which indicates that electricity is produced in the circuit. If we stop moving the magnet, then there will not be any deflection. It is at zero, which indicates that no electricity is there in the circuit. So it is clear that on moving the magnet near the circuit produces electric current. In contrary to this, if we move the conductor instead of magnet, then also the deflection of needle of galvanometer we can see, which again indicates that the electricity is produced when we move the conductor near the magnetic field. So altogether we can say that if we move the magnetic field near the conductor, or if we move the conductor in a magnetic field, produces electric current in the circuit. In place of permanent magnet, we can also use electromagnet. In the last episode we have seen about electromagnet, right? A coil of many turns. So this is the arrangement of electromagnet, and other side the circuit which we have seen just before. So in one coil we have used galvanometer to know the presence of current. In another circuit it is connected to a battery. On applying potential difference, the coil becomes magnet. We call it as electromagnet, right? So about solenoid we have already discussed. Here when you put on the switch, then the movement of the needle of the galvanometer we can see in the secondary coil, which indicates that here on applying potential difference, the first coil acts as a magnet. Here magnetic field is produced. Due to the magnetic field near the secondary coil, it induces current in the secondary coil. The current so produced in the secondary coil is what we call induced current. So I believe you understood what is induced current. When we talk about induced current, then there are two ways by which induced current could be produced in an electric circuit. Now either we have to move the magnet around a conductor, or we have to move the conductor inside the magnetic field. So in either way, induced current will be produced in the circuit. Now the question is, what will be the direction of induced current? To know the direction of induced current, we have another rule called Fleming's right hand rule. So in the last episode we have seen about Fleming's left hand rule, right? We have to stretch first three fingers right angle to one another. Likewise in Fleming's right hand rule also we have to stretch three fingers, first three fingers, thumb, forefinger and central finger, in such a way that all the fingers make right angle, or all the fingers are perpendicular to each other. Let us see the quantities associated with these fingers. In Fleming's left hand rule, forefinger indicated the field, that is magnetic field. In Fleming's right hand rule also, forefinger indicates field, that is magnetic field, and thumb indicates the motion. In case of Fleming's left hand rule, here also thumb indicates motion. Motion means moving motion of the conductor. Just before we have seen, on moving the conductor in a magnetic field produces induced current. So the direction of motion of the conductor is the thumb. The direction of the thumb indicates that one. And the central finger, in Fleming's left hand rule we have seen central finger indicates what? It is current. Here central finger indicates induced current. So by stretching these three fingers, assigning the quantities over each finger, we can find the direction. So once again, central finger is for induced current, direction of induced current, forefinger is for the direction of magnetic field, and thumb indicates the direction to which the conductor has to be moved in a magnetic field. Understood, children? Based on the principle of Fleming's right hand rule and phenomena of electromagnetic induction, a device is developed. What is that device? Do you know this? It is electric generator. So let us understand how electric generator works, and with diagrammatically we try to understand. Here electric generator works on the principle of electromagnetic induction. Previously we have seen that a galvanometer has been used to detect the current. So in the experiment purpose, the current so produced, the induced current so produced is very small, but in a commercial way also large amount of current can be generated by using electric generator on the basis of electromagnetic induction. Now let us see the setup of the electric generator. In an electric generator, mechanical energy is used to rotate a conductor in a magnetic field to produce electricity. Now look at the picture of an electric generator. This generator consists of a rotating rectangular coil ABCD, as you can see on the picture, placed between the two poles of a permanent magnet, here north pole and here it is south pole. The two ends of these coils are connected to two rings R1 and R2. Here it is R1 and here it is R2. The inner side of these rings are made insulated. Inside the ring, the surface is insulated. The two conducting stationary brushes B1 and B2, as you can see, this is the B1 and this is B2. These are the two brushes and are kept pressed separately on ring R1 and R2. The two rings R1 and R2 are internally attached to an axle. As you can see, this is the axle. The axle may be mechanically rotated from outside to rotate the coil inside the magnetic field. Outer ends of these two brushes are connected to a galvanometer, as you can see here, to show the flow of current in the given external circuit. So this is the external circuit. In this circuit, we have connected a galvanometer to detect the presence of current or flow of electric current in the circuit. When the axle attached to the two rings is rotated such that the arm AB moves up and the arm CD moves down in the magnetic field produced by the permanent magnet. So this is our permanent magnet. Let us say the coil ABCD is rotated clockwise, this direction. So this moves up and CD moves down. So this is the clockwise direction, right? Here, by applying Fleming's right hand rule, the induced currents are set up in these arms along the direction AB and CD. Thus, an induced current flows in the direction of ABCD. If there are large number of turns in the coil, the current generated in each turn adds up to give a large current through the coil. This means that the current in the external circuit flows from B2, that is brush B2 to B1. After half a rotation, you can see very well that C comes this side and B goes this side. So here B becomes C and C becomes B, right? Now here D becomes A and A becomes D. So after a half rotation, arm CD starts moving up, that is this direction, and here BA moves downward direction. As a result, the direction of induced current in both the arms change, give rise to the net induced current in the direction DCBA, that is this direction. The current in the external circuit now flows from B1 to B2. Earlier, the flow of electric current was from B2 to B1, right? Thus, after every half rotation, the polarity of the current in the respective arms changes. Such a current which changes direction after equal intervals of time is called an alternating current. The device is called an AC generator. To get a direct current, a split-ring type commutator must be used. With this arrangement, one brush is at all times in contact with the arm moving up in the field, while the other is in contact with the arm moving down. We have already studied about split-ring in electric motor. The main purpose of split-ring is it acts as a commutator, right? Here in electric generator also, split-ring, the purpose of the split-ring remains the same. So I believe you understood the principle and working of electric generator. As far as this chapter is concerned, some of the portions have been deleted for the session 2021. So the deleted portion also I'll display on the screen. Now look at the screen. So let us see the deleted portions from the chapter, that is magnetic effect of electric current for the session 2021. Electric generator will not be included in the portion. Direct current, we have not discussed about direct current. And alternating current, it is also called as AC current, and direct current is also known as DC current. So this is not required, so I have not explained about direct current and alternating current. Frequency of AC, that is frequency of alternating current, is also excluded from the syllabus. Advantages of alternating current over DC is also not there. Domestic electric circuits, this is one of the important topic, but it is not there in the syllabus, so I did not explain about domestic electric circuit. So these are the portions which are deleted from the chapter Magnetic Effect of Electric Current for the session 2021. So these are the deleted portions from this chapter for the session 2021. Let us now discuss some of the most important questions which are very often asked in the CBSE examinations. Let us see some of the most important questions. The first question is, what is an electromagnet? So we have already discussed about electromagnet, right? On what factors does the strength of an electric magnet depends? Now what could be the answer here? We have already discussed about electromagnet, right? So here an electromagnet, it can be defined as a soft iron core placed inside a solenoid behaves like a powerful magnet. This is what we have discussed, right? When current is passed through the solenoid, this device is called an electromagnet. Dear students, for reference you may take the snapshot of the question answers what we are discussing. Now let us see the second part of the question, that is, on what factor does the strength of the electromagnet depends? We have already discussed this too. The factors on which the strength of an electromagnet depends are: number one, we have learned that the number of turns in the coil increases the magnetic field. So by increasing the number of turns in the coil, the strength of the electromagnet can be increased. The second factor is the strength of the current. If the current flowing in the circuit or in the coil is more, then the strength of the electromagnet will be more. And the third one is nature of the core material. The core of the magnetic material, like soft iron, increases the strength of the electromagnet. So by taking the nature of the material into consideration, we can increase the strength of electromagnet. So these are the three most important factors on which strength of an electromagnet depends. Now see the second question, when is the force exerted on a current carrying conductor is maximum and minimum? This also we have already discussed, just let us have the answer. When the current carrying conductor is held perpendicular to the direction, we have learned in Fleming's left hand rule that here suppose it is the magnetic field and here it is the current. We have extended first three fingers, that is forefinger, central finger and the thumb right angle to each other, right? So when the current carrying conductor is held perpendicular to the direction of the magnetic field, then the force exerted will be maximum. The next part is, when is the force exerted on a current carrying conductor is minimum? When the current carrying conductor is held parallel to the direction of the magnetic field, in that case the force exerted will be minimum, or we can say that the force will be zero. So do remember the condition on which the force exerted on a current carrying conductor will be maximum and minimum. Now let us see the third question. The third question is, how can the speed of the rotation of the armature coil of an electric motor be increased? Now we have discussed about electric motor, right? The armature coil rotates when the current is applied. When will be the rotation, the speed of rotation of the armature increase? Here the speed of rotation of the armature coil can be increased by increasing the strength of the magnetic field. If we increase the strength of the magnetic field, then the rotation caused by the armature will be more. The second factor on which the speed of rotation of the armature depends is the number of turns in the coil. If we increase the number of turns in the coil of the armature, then the speed of rotation will be more. And the third factor on which the speed of rotation depends is the current in the coil. If we pass less current in the coil, obviously the movement, the speed at which the armature rotates will be less. If we pass more current, then obviously more current will flow in the coil and the force exerted will be maximum. So the speed of rotation of the armature coil will be more. So this way we can increase the speed of rotation of the armature coil of an electric motor by increasing these three quantities. Now the fourth question is, what is the role of split ring in an electric motor? This also we have already discussed. The split ring reverses the direction of current in the armature coil after every half rotation. This is what we have learned, right? When the current flows in the fourth side of the arm of the armature, it is pushed downward, whereas when the current enters from other side, the direction of electric current will be different. So in that case, the arm will be pushed upward direction. So on half rotation, the reversal of current we could see, right? So it is done by the split ring. So we can say that the split ring reverses the direction of current in the armature coil after every half rotation. So it acts as a commutator, right? So the main role of split ring in an electric motor is it acts as a commutator. The reversal of current reverses the direction of forces acting on the two arms of the armature after every half rotation. This allows the armature coil to rotate continuously in the same direction. Got it, children? So dear students, that's all we have for today's session. On the basis of today's learning, I would like to give some easy home assignments which you can practice at home. Here is your home assignment. The first question is state Fleming's left hand rule. Very straight question. We have already learned the quantities associated with each fingers. So by stretching the fingers, by identifying the quantities, you can easily define the Fleming's left hand rule. Now the second question is, what is electromagnetic induction? Very important question, and the definition you by heart it. So this is also very simple question that you can do it yourself. Now let us see the third question. What is the function of a galvanometer? We have discussed about galvanometer in detail, so you have to write the function. The fourth question is, what type of magnetic field is produced due to a straight solenoid? So think about the solenoid and magnetic field, how the magnetic field, think about the poles, think about the diagrams, then you will find the type of magnetic field produced in a straight solenoid. Now the fifth question is, an electric generator converts dash energy into dash energy. So when we talk about electric generator, at the end of this session we have discussed about electric generator. There I have told you the energy transformation, right? So here you have to write which energy is converted into what energy. And the second part of the same question, it works on the basis of dash. On what principle or on what phenomena the electric generator works? So this also very simple question. Now you see the sixth question, dash is the phenomena in which an electric current is induced in a circuit because of changing magnetic field. Very simple question. So these are the home assignments which you can try. Hope you will do all these home assignments very easily. See you all on another day with a new chapter. Till then, take good care of yourself. Bye.